Welcome to this session of Shadow the Scientist, Astronomy Night at the International Gemini Observatory North. My name is Jamika Marshall, and I'm pleased to serve as the Shadow the Scientist Coordinator. The Shadow the Scientist initiative is housed under the Creating Equity in STEAM umbrella of programs offered by a team at the University of California, Santa Cruz. The International Gemini Observatory consists of twin 8.1 meter optical infrared telescopes located on mountains in Hawaii and Chile, enabling the telescopes to collectively access the entire sky. Gemini Observatory utilizes the Q observing mode, in which science staff take observations on behalf of science teams worldwide. The staff determine the conditions on the ground and in the sky, as well as the scientific priorities, and choose from a pool of scientific programs to observe. In this session, we have the privilege of shadowing the Gemini North observing team members Brian Lameau and Matias Rodriguez. They will be using the Gemini North telescope located near the sun of Maunakea on the island of Hawaii, with the observations taking place remotely from the control room and the Hilo Base Facility. Our guide on this cosmic journey is another member of the Gemini Science and Observing Team, Zachary Hartman. Hi, Zach.
Hi, Jamika. Thanks for that great introduction. Yeah, so we are currently observing some high humidity. So unfortunately for everybody, we are not observing right now. The weather looks great. It looks absolutely gorgeous. So if I go to this, so this is actually the Keck cloud cams, and the weather looks absolutely gorgeous. But then if I go to this screen, the humidity is 100%. And on top of all of that, we have another lovely situation where a couple of days ago, the Kilauea volcano started erupting. And so this is a GEO satellite image taken a couple days ago, and you can see the black dot on the bottom of Hawaii. That is Kilauea starting to erupt. It's since stopped erupting, but it's still emitting a lot of particles, and so our particle counts are very high right now. So even if it was within our realm for humidity, we are unfortunately closed due to particle counts. So yeah, but we're here at Gemini North, and in the control room we have Brian and Matthias. So if they want to say hello, please do so.
Hey, Zach. How's it going? Long time no see.
I know, right?
Hi, everybody. Aloha. My name is Brian Lameau. I am one of the staff scientists here. I'm the observer for this evening. I am in charge of all of our instruments here at Gemini North. I am the one choosing the observations that are going to be taken tonight. And I'm here with Matthias, who is our operator for the night. Do you want to introduce yourself, Matthias?
Sure thing. Everyone, my name is Matthias. I'm here at the side of my good friend Brian. Unfortunately, Zach said we are closed for the night. Otherwise, I will be slewing the telescope to all directions, getting some science as an operator on this side of the room. And yeah.
Yep, so we're in our base facility here at Gemini North. This is where graduate student visitors come first. This is in Hilo, which is on the big island of Hawaii on the east side. And we're basically at sea level here. So we have a connection up to the Maunakea, which is about 4,000 meters. And Matthias has 8 screens here that he uses to control the telescope. So the movement of the telescope, the movement of our wavefront sensors, the dome, the motors associated with the dome. Most of the mechanical aspects of the telescope are controlled over on this side of the room. The instrumentation aspects of the observations are controlled on this side of the room. So I have 8 screens here. This is all to assess the conditions in the sky and choose the appropriate observations for those conditions, to keep an eye on the telescope, to understand where the light is being sent, to set up observations, to queue up observations and to execute observations, to analyze the data that come out, and then make sure all the instruments are behaving as they should. So maybe Zach, you can walk us through some of the screens that I have up. And so for everybody that's here, we're really doing the session for you guys. The chances that we open up are not high. It's 3:10 in the morning here in Hawaii. Our observations are slated to finish around 4:45. So we have about another hour and a half that's possible for opening. But currently, as Zach said, the particle count is too high and the humidity is too high. So we're not going to be doing real observations, at least now. So, we have plenty of downtime. Feel free to ask questions, anything that you're interested in, share your science or your observations that you've taken with Maunakea telescopes or other telescopes around the world. If you have any questions, there's a lot of expertise here about observatory life and other aspects of observatories, about, different people coming from different backgrounds, different cultures. So please feel free to introduce yourself and ask any question you would like in the chat, or if you'd like to do it verbally, you can just raise your hand and we can call on you.
Yeah, don't worry about interrupting us, so because we'll keep talking if we but yeah, so again, if you have any questions, let us know. I can show off some of the screens that we would be looking at normally if we were observing. So if I go over here, so if you were to come and observe at Gemini North, this would be a screen that becomes very familiar with you. This is what we call the Telescope Systems Display Screen, the TSD. And on it, there's a bunch of information about the current status of the telescope. So, starting at the top, there's a bunch of information on where the telescope's pointing, what the time is in both UTC, Hawaii time, and in Chile. And actually, one of the monitors in the main control room, it has just the time for both sites, Gemini North and Gemini South. It also has what air mass you're pointed to, what the seeing is given in the guider that you're looking through, and I'll get to those in a couple minutes. And then at the bottom here, you can see a lot of different display screens for the telescope. So there's on the left, there's an image of the dome, and if the dome was open, then you would see a mock-up of how far the dome is open and where we're pointing, if we were pointing at somewhere else other than zenith. Then as we go across to the right on the bottom, you have the 2 wraps for the telescope. So the telescope is moving along on conveyors, and at a certain point we can't go any farther, so we need to slew the other way around. And so this tells us that information. And then as we go one more further, this is just a diagram saying where the light is going. So if we were open and the mirror cover was off and we were taking data, you'd be able to see the light path. And actually you can see the light path right now at the bottom. So because Brian has set up some daytime calibrations for GNIRS. And so you can see that GCal, which is our calibration unit, where all the arcs and all the light sources for those are in that GCal unit. And so we're sending the light from GCal over the GNIRS for these daytime cals, and we'll see those in a bit. And then finally, in the lower right over here, we have the wavefront sensors that we use. So for every single Gemini observation, we have a guider. And a lot of you have probably seen this in the OT and our observing tool. And so different observations use different guiders. For example, GMOS primarily uses OI. GNIRS uses P2, MAROON-X, P2. GNIRS can also use the AO system, ALTAIR, which is the AO WFS. And then Alpeke, which is in GCal and as our speckle instrument, uses P2 as well. So P1 is not really used; it's more there as backup in case something happens with P2. But we use these guiders to both guide on target to make sure the telescope is pointed and maintains its pointing, but also is there to correct some of the atmosphere. And so if I go to a different screen here, we go to this one. So this kind of shows off a couple different things.
Sorry, Zach, I'll just mention one thing, which is that we do have this super seeing mode at the observatory, which is called LGS plus P1. And that's the main use, I think, of P1 at this point. You're right that it's like kind of a backup peripheral wavefront sensor, but with LGS plus P1, for reasons which escape me at the moment, we do use the P1 sensor. And this is to get wavefront corrections, so basically non-local wavefront corrections. So normally LGS or NGS mode, laser guide star, natural guide star mode, you're making wavefront corrections with our AO system ALTAIR right at the location of your target. This LGS plus P1 allows wavefront corrections up to about 6 arc minutes away from your target. So that opens up a much larger field of view, because with NGS and LGS, you really have to have something super bright close by your target or as your target. And so you can look almost anywhere in the sky because there'll be a bright object within 6 arc minutes of your target for almost every target in the sky. And then you make corrections at the P1 location, and they're not going to be perfect because they're not on axis, but they're going to improve things quite a bit. And so this allows you to make the tip tail correction with the P1 star, the higher order corrections with the laser guide star, and you can improve the image quality by about a factor of 2 to 3. So like, let's say your natural seeing for the night was 0.6 with LGS plus P1, and this is only for near infrared, but with LGS plus P1, you can get to like 0.2, 0.25. So almost AO level corrections, but not quite. But it can improve science quite a bit.
Yeah, it's been a while since we've used that, so I forgot about that.
Yeah, it's such a cool mode. I really hope it comes back soon, because our laser is not fully working at the moment.
But yeah, so with the wavefront sensors, we have these tools on the screen that we use to kind of monitor what's going on with them. So the two at the top show the astigmatism and tilt readings that we get from the wavefront sensors. And basically, we are able to correct for small order aberrations from the atmosphere. And so these are the two monitors on that, and being able and showing how much corrections are being applied over time. And then on the left-hand side of these plots, not the top two, we have what we get from the seeing, which is this middle left plot, is the seeing that we get from OI. And then the bottom is the counts that we get from OI. So we can monitor, what the image quality is over the course of an observation, and we can keep in track of, the counts, especially if we're going through clouds. We can keep track of how the counts are dropping, going back up, and making sure that we're taking the best data possible. The other two plots here show weather information. The bottom one is the wind graph, and you can see that it's not that windy of a night. But then the bad news comes from the middle right plot, which is shows our temperature, our wind. There's also another measure of wind speed, but it also shows the humidity. And so the blue, the pink, and the orange lines up here show the humidity values over the past 30 minutes. And as you can see, they're all above 90-ish. And so for Gemini, our closing limit for humidity is 85%. So once it goes above 85%, we have to shut everything down. We have to close the dome. And then in order for us to open, we have to be below 75% for an hour. And that does not happen tonight. So this leads to us being closed for pretty much the entire night tonight. So those are the guiders. Let's see here. So this screen kind of shows off how we execute these observations. So I've seen in the chat a number of you have designed observations and have some observations, particularly with GMOS and MAROON-X. And so in the OT, you're communicating with a contact scientist over the course of when you're setting up these phase twos and setting up your program within the OT. And so when you're going through that, the reason we really want that to be a smooth process is because effectively at night, Brian's going to take those sequences that you all have set up in the OT, and he's just going to run them through the sec-exec. And so we don't want him at night to discover an issue with the program that would cause time to be lost or problems with the instrument. And so that's why we have contact scientists there to help set up your program and make sure that the program's set up correctly after you have set up the program in the OT. So if we go down to this screen, so this is actually, I saw someone, now we've changed.
I literally just brought that up, so good timing, Zach.
So one of you, I believe it was Jennifer, mentioned MAROON-X. So MAROON-X has been a visitor instrument. And so it cannot be run through sec-exec. And so actually this is a VNC into the MAROON-X software where we would run MAROON-X normally. And so at the bottom here, you actually see some calibration data taken during the day, which has the Etalon laser and the laser frequency comb, and also the different parameters that we use for that observation, or for that calibration, sorry. Oh, and now we're changing everywhere. Unless that dropped. Oh, I think I got kicked out. That's interesting. There we go. Now I'm back. But the thing about MAROON-X, Bruno, we were gonna go through some of the DayCal stuff at a certain point. I don't know whether Brian had any more of the DayCals set up.
Yeah, we can do that. You want to just run through like the rest of MAROON-X and maybe any other screens that are of interest, and then I'm happy to go do some DayCals. It looks like people have experience with GMOS mostly, so I can set up. I can set up a GMOS I can set up something for GMOS. Well, maybe we can do GNIRS first, and then we could go to GMOS. It would just be like arcs and flats, but
Yeah.
still we could see something.
Yeah, so I was just going to finish up with MAROON-X. Here we show MAROON-X is a fiber-fed instrument. And so unlike a lot of our other instruments, which are on the instrument cube on the telescope, there's just a wire that comes, there's just a fiber that comes off of the instrument cube and goes down into the bowels of Gemini and eventually makes its way to MAROON-X stored down in the basement. Well, not in the basement, but in the lower levels. And so that's where MAROON-X exists. It's not on the telescope. This allows it for higher stability and in order to reach the radial velocity precisions that are needed for the exoplanet observations. So let's see here. What other interesting I think for the moment
go to the
with
QPT, Zach, if you want.
We could, or we go through that afterwards. But
we could also go to the ISDs that are up on screen 6.
the ISDs would actually be a good thing. So the ISDs are basically our window into the instruments. So basically these are instrument status displays, much like the TSD, the telescope systems displays. And so this shows all the moving parts within the different instruments and shows what they're doing and whether there's any issues with them. As you can see, everything is green, so it's very good. If there were issues, there'd be flashing red lights, maybe yellow. But also as we start the decals and everything, things may shift around in here. So you'll see shifting parts, different name changes as different filters are moved in, different gratings are moved in, whether it's an IFU or whether it's a long slit. Those different things all take place. We all see those changes happening on this ISD as we go through the night, and we're taking different observations with different setups. And so we're talking about decals. So if I go back over to here, which screen do you want me on, Brian?
As you like. I think maybe let's go to screen 2.
Okay.
Three.
Yeah, exec, or nope, that's your
The OT.
Yeah, so Brian's right now checking out, setting up some flats and darks for us so that we can observe them. And so this was within his workshop that he has on the OT, so that he can check stuff. If we're all contact scientists here, so if we have observations that are particularly tricky, or we want to remember how a particular observation is set up, we can save it within our OTs so that we can keep that in mind for next time in case we encounter this program again. And so that's a majority of what I believe Brian's targets are in his workshop. And so he's set up this program, this short little flat and arc observations for us.
Yeah, so I can explain what we're seeing here. So I guess some of you have already interacted with the observing tool. See, Larissa, you at least got some data observed with GMOS, so maybe you have some observing tool experience. And seems like actually everybody has done at least some interfacing with GMOS data, so maybe this is kind of familiar to you. But just to run through, in case you haven't seen it or you don't remember, it's a very complicated tool with a lot of clicking, a lot of different moving parts, but it's pretty amazing. So basically, as Zach mentioned, anybody in the world, that's working on a program, they can set up their observations. We have templates that we use to set up different types of observations, and then you modify those templates for the science that you're interested in. So changing around the configuration of the instrument that you're using and the wavefront sensors for your needs. Then we as contact scientists, so like Zach and myself act as contact scientists, we check those observations that you've set up in this observing tool. So you sync things. So you say, okay, I'm ready. I sync. And then you say, okay, contact scientist, why don't you take a look? And then we go through a checklist of, probably tens, if not hundreds of things that we look at. And we send you back suggestions and say, well, maybe you want to change this grading to this grading, or maybe that guide star that you're using is not the greatest guide star in the world. Or maybe you want to use the average parallactic angle instead of a fixed position angle, so on and so forth. And so once that process is done, usually we go through about 2 or 3 iterations of that. We get to the point where we say, okay, looks like everything's ready, so let's get it ready for the queue. So we have the magic ability to set things to prepared, and that means it goes into our queue. So at that point, the observation is basically fixed, and it's ready for ingestion into our queue. And so then our staff that coordinate that queue, they pick different observations that they think are appropriate for a given night, and then provide that information to myself as an observer. And then we choose as an observer the best combination of those observations that the coordinator has set up that are for conditions when we're open. So currently, the best observations that we can take for the current conditions are day cals. So lucky you, Bruno. So this is a long slit. It says science with GCal flats and some random collection of letters afterwards. But in fact, I've just set this up so that we're taking GCal flats and arcs. That's it. So no science, which is good. Let me actually change the target here so we don't confuse the telescope. Okay, so this should go to GCal. So I'm going to queue this up. So if you could see all of my screens now, so now I've queued into our sequence executor this GMOS observation. And so Zach kindly just switched over to that screen. So I'm going to load this sequence, Brian 84. And we have a bunch of different steps here. So you can see we have flats and arcs interspersed with one another. We have something called smart GCal. So it's basically a table where for a given observation, we have the central wavelength, we know the disperser. So here the disperser is the R400 grading, and the central wavelength is 768 nanometers. We have the order blocking filter OG515 in, and we have the focal plane unit being the 1 arc second wide long slit. And so for that given set of optical elements and configurations, we have a table that says, okay, here's how long the exposure should be for a flat. And so we don't actually have to set this manually, which is nice because it would take a lot of guessing to do that. And that's not something that we want to do. This should be very quick. These are just calibrations that we would take at the end of the observation. So we want to make that as quick as possible. So now we have these different options here. This is the telescope control system. So this is, right now we're not going to be moving the telescope, but we have a deployable tertiary mirror, which Zach showed earlier, that takes the light from the GCal environment or from the sky and pipes it to one of the instruments. So if I press this TCS button, that deployable tertiary, and maybe Zach, you could bring up the TSD window, is going to move from piping the GCal light to GNIRS to GMOS. So this, you can see this blinking here. The mirror is actually turning, and it's directing the light from GCal into GMOS, so into the pupil of GMOS. So this is very quick. We just switched instruments, and this is what we do all the time at night. And that entire process took whatever it was, 20 seconds. So that's one of the amazing features of Gemini. So now I can configure the GCal environment, which basically means to turn on, in this case, a quartz lamp. So press that button. And right now the quartz lamp is warming up and then is eventually going to turn on. And there it is. And then, Zach, if you want to go over to the, oh, you're there already. You read my mind. Okay, so I'm clicking on GMOS North now. And you can see all these optical elements flashing. So you can see GCal, it recognizes that GCal is where GMOS is pointing. The quartz halogen lamp is on. We have the light going through all of these optical elements and then arriving at the detector here. And so we're changing the mask or the focal plane unit to the 1 arcsecond wide long slit. The two filter wheels are in place. So we have the order blocking filter and an open position for filter wheel 2. And there's 2 filter wheels just because we can have more filters that way. So one is usually always open. In fact, I think one is always open, and the other one, whichever filter wheel the filter requested filter is on, that's the one that's at that location. The grading turret is moving right now, so it's moving and also tilting the grading so that it's at the requested central wavelength. The shutter is currently closed because we don't want any light going in, any stray light going in at the moment. But as soon as everything is configured, then I'll take the observation. The shutter will be open for the time of the observation, expose the detector to the GCal light, and then close back up as soon as we're done. So I'm going to press the play button, which is the run button on our sequence executioner. And if everything goes well, GMOS will respond. The shutter opened just for a second there, and the detector got the light, and now it's reading it out. And so
Sequence paused.
okay, so the detector just read out. And I'm going to be on screen 5, I think. So this is, oh. Zach, are you in interactive mode?
Nope, not that I know of. I can go check. Nope, maybe I was.
Okay.
That's weird. If you open a VNC on different windows in Keeper, it it can have different interactive modes, apparently. Sorry about that.
No problem. Okay, so this is IRAF environment to analyze data. That's right, I said IRAF. So I have DS9 open, which probably you're all familiar with. And it's now tiling the 8 extensions of the multi-extension fits file that is a GMOS observation. I think it's 8, maybe 10. And here we go. And so that's a flat observation. So you can see the counts are, so this value up here, they're in the neighborhood of 25,000 to about 1,000 on the very bluest end. So I think red wavelengths over here, blue wavelengths over here. and we want like, roughly 1% error for the flat. So 10,000 counts is trying to get. So that looks good. That looks like a flat to me. So I'm happy with that. And we can then run an arc. So I'll go back up to our sec exec.
It's paused.
Okay, so that was a little bit longer. The arc lamps are a little bit dimmer. I'm not sure which arcs do we have. So copper argon. And let's see, so bring that up in same screen. Okay. So there is an arc observation. So these are all the arc lines. You can see it's red optimized. So again, red is over here. This is the dispersion direction. Wavelength dimension is on the x-axis. The spatial axis is the y dimension here. And we have a bunch of copper and argon lines. The density of those lines is quite high in the red and then falls off to the blue. So we may use different elemental lamps if we were trying to blue optimize. And right here we have software that very kindly flags saturated pixels. So there's a band right here, or a line right here that's flagged as being saturated. Here as well. Normally, we would worry about this when there's saturation of the data, because once the data gets saturated, you lose effectively all information. But when you're doing arc lamp exposures, you have so many other lines to create a wavelength solution. You basically just clip these portions out, and you can create a wavelength solution from the unsaturated lines. The reason why these are saturated is we're trying to pull out the fainter lines. And so we need to have the exposure time be fairly long to pull out those faint lines. And the cost of that is having a few brighter lines that are saturated. So this frame would be used for wavelength calibration. The flat would be used for slit tracing and response correction. And then if we were on sky and it was requested, or as a baseline, we might take a spectrophotometric observation. So supposing you need flux calibration for your observation, you want to get a line flux, for example, we would take a calibration star. So we would pick a star, or you would pick a star from as a program standard, and we would slew to your star right after we took the observation, or sometime during the semester if it was just a baseline standard. And then you could calibrate on an absolute scale the observation. So those are the three basic calibrations that we take for GMOS. arc, internal flat, and then spectrophotometric baseline standard. Okay, so great question, Bruno. So we don't actually do so some observatories do like dome flats, for example. We don't do that here. We do this all in the GCal environment. Yeah, thanks, Zach. So we do this all in the GCal environment. So it's really just our tertiary mirror here. We have, let me see actually if I can bring up. Okay, so here's GCal. Heartbeat is good, so it's working. And here's all the things that we have in GCal. So we have the quartz halogen, we have the IR diffuser lamp, we have the argon lamp, xenon, thorium argon, copper argon. So each one of these could be used for a different central wavelength, different disperser. As I mentioned, we can turn on and off different elemental lamps depending on the central wavelength and the disperser that we're using. In this particular case, our smart GCal lookup table has determined that copper argon is the appropriate lamp to turn on. So you can see this is on currently. As soon as I configure everything, pressing the buttons that I just pressed earlier, the GCal environment wakes up and there's a signal that's sent that says, okay, turn on this lamp. Our tertiary mirror moves such that that light that comes out of that GCal environment gets piped to whatever instrument we're wanting to calibrate. And so this is all done at the bottom of the telescope. So if you're actually looking at the telescope, so if you were up on Mauna Kea and you were looking at the telescope, there would be this big instrument cage at the bottom of the telescope that tracks with the telescope. So just sitting behind the primary mirror. And so the light comes in from the top, it hits the primary mirror, goes secondary mirror, down into our Cassegrain instrument cage. But when we're doing the calibrations, it's just light from GCal shot into whatever instrument we want to use. So in this case, it's truly all internal inside the CAS instrument cage. GCal light is piped to GMOS through reflection on the tertiary mirror. While I'm here, I can turn off our copper argon. And so you can see on the display there, now there's no light coming out. Yep, so no more light coming out of the GCal environment. What we could do now is we could do a GNIRS one. Feel free to interrupt, ask questions. Anything you like, we're just kind of going through the motions. It looks like it's still 95% relative humidity, although the particle counts are dropping, Matthias. Are you optimistic? Finally. Okay, so right, so I'll queue up a GNIRS observation. So this will be a cross-dispersed GNIRS observation. Clean up that last one. Yeah. Sweet. Okay. So, yeah, if you bring up the Firefox window in screen 2. This is GNIRS. This is the instrument that I helped to run here at the observatory. So I'm one of two instrument scientists for the GNIRS instrument. And I use this diagram a lot. And this is when I was in grad school and when I was a postdoc. And before I came to the observatory, my eyes would glaze over when I would see a diagram like this. But actually, this is super helpful for me now to keep track of where the light goes in GNIRS. And we have optical diagrams for effectively all the instruments. But GNIRS is a quite complicated near infrared spectrograph, an imager, or it pretends to be an imager. And as a wise person once said, there's just too many moving parts. So here are all the moving parts. There's a filter wheel, just like in GMOS, and there's actually two filter wheels that contain broadband filters and then order filters, so order sorting filters, and our cross dispersed filter, which allows basically all the light from 1 micron redward. We have a Decker slide, which is basically open apertures that block out straight light. We have a slit slide that has 10 different slits, or sorry, 7 different slits, 1 acquisition position, and then 2 IFUs. No, 8 different slits, okay. So this is what determines basically which light can enter. And then once the light enters, there's all these different configurable optical elements. So we have an acquisition mirror if we're acquiring on a target. If we pull this acquisition mirror out of the optical path, then we have our dispersive elements. So this is a prism here, which we can use as cross disperse. We have a mirror actually on the prism, so we can basically take the prism out of the optical path if we want. So basically we can choose to use the prism if we want, or not if we don't want. Even if we remove the acquisition mirror, then we have a grading. So if the acquisition mirror is removed, undeployed, whatever, then we are always using a grading. And so we have 3 different gradings here. And then we have, well, right now we have 3 different cameras in GNIRS. One is broken. The short red one is broken. We have short blue, we have long red and long blue. And so the longness or shortness refers to the focal length. We just increase the focal length for the long red and long blue cameras by having a set of mirrors that increases the path length. And so, as you know from Astro 101 or Astro 10 or Astro 1, whatever your system is, you increase the focal length, you increase the magnification. And so these are for higher resolution observations. Our high resolution integral field unit uses both the long red and long blue. If we want to get higher spectral resolution, that would be long red and long blue. If we're doing imaging with adaptive optics, we would use long red, or well, we would use long blue because our AO system doesn't work. And so red here means redward of 2.5 microns, so redward of K band. So L and M band observations are taken with long red in our adaptive optic system. I don't think any adaptive optic system in the world works at these long of wavelengths. And then long blue goes from sensitive from about 0.8 microns. In actuality, probably 1 micron or 1.1 microns, all the way to about 2.5 microns. So this is the optical diagram for GNIRS. And so I just wanted to show that to y'all so it makes a little bit more sense what we're doing. So maybe we can go over to the ISD, Zach. Cool. Okay, so I'm loading up the sequence now. So same thing that I did before with GMOS. I'm just going to do the same with GNIRS. So I'm going to configure GNIRS now. And so actually, since we already took observations with GNIRS earlier in the same exact configuration, none of the optical elements moved. But if you go down to the ISD, or sorry, if you go to the TCS, sorry, Zach. ESD. It's too early in the morning. Yeah, so I'm going to configure the telescope control system now, and we'll see the deployable tertiary. It's going to start to move. I'm going to turn on GCal, so you can see now that there's light coming out of GCal, but we don't want it going into GMOS, we want it going into GNIRS. So the mirror is going to move back to the location that it started off as. Okay, and so we're now in position. So the light is, so we have the IR diffuser lamp on here, and the light is being piped to GNIRS. So we can start to take an observation. Actually going to start with this one. So, yep, so I take the first observation. These reconfigure because I just changed the setup a little bit. And this is an IR observation, so we have a lot of light. There's a lot of thermal light, and we don't have to do much. This is just a flat, so just 2 seconds is enough to take an observation, get plenty of signal, and the IR detectors are much faster to read out than an optical CCD. So already we have our observation, and this was number 17. Okay, so this is a cross-dispersed observation. So this is just a flat, and okay, so there's probably going to be like 2,000 or 3,000 counts, which is good for GNIRS. We start to move into nonlinearity around, well, it depends on the exact mode, but around 5,000 counts. So this is probably around 2,000 or 3,000 counts. And what you see here is a cross-dispersed spectrum. So we're using both the prism to disperse along the X dimension and the grating to disperse along the Y dimension here. So the reddest wavelengths are down here. This is the K band, roughly. So 2.4, 2.5 microns is going to be around here. And then the bluest wavelengths are going to be over here. So this is roughly X band, maybe even into like Y or Z. So probably 0.9 microns is somewhere around here where we can barely see it. And if you're taking a scientific observation, the chances that you're going to get any meaningful signal in like this order here are very, very low. So the orders that are the most sensitive are K through J, basically. So about these first 4, or maybe 5. And so that's where most of your scientific leverage is. But wonderful thing about this mode is that you get all of the orders at once. So you can get all the information for a single object from K band all the way to X band at the expense of having a fairly short slit. So this is a 7 arc second slit. We have a long slit mode that is with the short cameras 99 arc seconds. So there are certain targets that that's better for, but you only get a single order at a time. So you get K band or H band or J band or X band. But cross dispersed is the most commonly used mode because you get all of the orders at once. And then let's see, you can take an arc. So I'll configure GNIRS again. So this is just turning on one of the arc. Right, so we have arc lamp on. So we have the argon lamp on now. And you can see again, it's a very, very short exposure. This is great because we usually take these on sky because we want to be in the same exact location for flexure purposes as we are for the science. And so did the arc lamp actually come on? Let's see. Every once in a while, it doesn't come on as fast as we'd like it to. It didn't. Ooh, okay. So this is something I would check when I'm an observer to make sure that the lamp came on fast enough so that we got the calibration data that we would need. And so it appears not. This is basically noise plus persistence. So this is just readout from the previous flat observation. So I am going to try again.
Sequence complete.
There we go. Great, so that's what it's supposed to look like. So it just took a little bit longer for it to warm up. We haven't been using GCal very much in these last 3 days. So it was a little bit lethargic. Don't blame it, it's 4 in the morning. But yeah, so this is how you do the wavelength calibration, just the same thing as GMOS. So we have argon lines that are of known wavelengths. And you use the flat to trace the location of the signal, and then once you have your 2-dimensional spectrum, that's wavelength axis, spatial axis this way, you can just pile these on top of each other in a big array, and then you can match up the known wavelengths of these lines with the locations in the detector to get a wavelength calibrated spectrum. So that's what we do on sky after every observation that we take with GNIRS that's spectroscopic. And we also always take telluric standards. So telluric absorption features in the atmosphere are difficult to deal with in the infrared. They change on very short timescales. They change as a function of air mass. So we have to take observations that allow you to calibrate this out. Usually we use stars that have very regular features like A0 stars that have, you can make a template. You can scale the observations to that template, and then you can see any decrement of flux that's present. That's due to the telluric absorption. And then you apply that effectively that ratio to your scientific observations. So yeah, Jennifer asked if we always take tellurics for all instruments or just this one. So tellurics are actually telluric features in the optical are not that bad. You can basically model them out with very high precision. Based on the air mass. So there's only 2 real telluric bands in the optical. They're depending on the central wavelength that you use, you may not even observe them. And so basically you just use a template to model it out. In the IR, especially with cross dispersed, there's so many telluric features. They vary very rapidly, and they're not super predictable in terms of air mass. It's debatable. Some observatories do use a template-based approach. There are people at this observatory that are working on trying to find a good template-based approach, but we require that the precision and accuracy that we recover from that template-based approach is the same as what we get on sky. And that's a very difficult metric to live up to. So there is work ongoing, and there's some hope that eventually we'll not have to take tellurics. But for now, we're taking tellurics with every IR observation. And since GNIRS is our only IR instrument in the north, GNIRS is the only instrument that we take tellurics for. Yeah, so the templates. So like I said, when you take a telluric observation, maybe you would take an A0 star, so A0 dwarf. So very regular features, just the Balmer features of known depth. You could take like Vega, for example, so the measured spectrum of Vega, or a model of an A0 star, main sequence star. And you can just scale that template to the observation that you have. So we take an observation of a star that's 6 magnitude, let's say, or let's make the math easy, 5th magnitude. So then we just scale the Vega spectrum by a factor of 100, and then we see that oh yeah, there's decrements at this wavelength, this wavelength, this wavelength. So we can then remove, or basically ratio out any loss of flux due to the telluric features. So if you take an observation of a source that has a known SED, spectral energy distribution, so let's say you take an observation of a quasar. A lot of quasars look alike, at least in certain portions of the rest frame spectrum. And so you can use, you don't necessarily have to take a telluric, because there you can effectively do the same thing. You take your template of a quasar, you scale it to the observation that you're taking, whatever quasar you're looking at, and then you look for decrements in flux, and then you take the ratio and basically cover the lost flux. Yeah, I don't. So the question from Jennifer was about the removal of the telluric absorption due to templates. I know that in data I've reduced from other observatories, that is very definitely the case. I assume that's the case with like dragons, for example. I don't know, Zach, have you done a GMOS long slit reduction with dragons or Gemini IRF?
No, I'm trying to figure it out. I'm searching the Dragons page right now.
My guess is they do something. But again, it's pretty standard to do that. I would be super surprised if they didn't at least make an attempt at it. Because there's the A band and the B band and the optical, which basically scale really easily with air mass. So once you know the air mass of your observation, or the average air mass, or if you want to correct per frame, whatever, then you can just scale a telluric template by the air mass. So zenith telluric template by the air mass, and just make a correction, right? And those data are like in that wavelength range are suspect. I mean, you wouldn't want to do like, base all of your science on that. But it does usually do a fairly good job. I'm speaking from experience with like GMOS on KEK and LRES on KEK, which are either long slit or multi-object spectrographs. I've done a lot with like telluric correction based on templates, and it seems to do pretty dang well. So the answer, Jennifer, is I don't know. And I don't think Zach has an answer. There's an entire group of people here called the Science User Support Department that developed the data reduction pipelines. We're not involved with that except as users. And I've actually never taken GMOS observations for my own science before. I did just propose for 24B to do that, so I could give you an answer if my proposal is accepted in like 3 months, but yeah. So we are at 4:10. We have about 40 minutes until 12-degree twilight, so when the sun is 12 degrees below the horizon. In order to open up, as we mentioned earlier, we need to be below 75 for 30, 40, 45 minutes, depending on exactly the night, how volatile things are. And so it's on top of that, we would have to do a dome drain, which means we have to check for water in the dome so that water doesn't get on the primary mirror if it's trapped somewhere in the dome, which takes anywhere between 20 minutes and an hour, depending on how much water might be trapped in the dome. So basically, it's mathematically impossible for us to observe tonight. So it seems as though, unfortunately, despite the very beautiful skies above Maunakea, that we will not observe for now the third night in a row. We were really hoping to get you guys a night where you could actually experience observations, but it appears that it won't be tonight, unfortunately. I will mention that we do these Shadow the Scientist sessions very regularly. So we have another session coming up it's the 6th. So 5 days. There's a public session. You can put the link in the chat. You're very welcome to register for another session where we could actually do some observing. I guarantee you is pretty awesome. We had some pretty awesome observations planned for the end of this evening, so I'm super bummed we didn't get to show you guys that. But yeah, there'll be another public session on June 11th with Gemini North. There's a Keck Shadow the Scientists coming up actually tonight. So one of my collaborators will be on the Keck telescope. So of course you're welcome to watch those. And then I think we're doing another Shadow the Scientists on July 22nd, which is to show off what will be our newest facility instrument, IGRNS 2. Actually, Zach, did you want to talk a little bit about IGRNS 2? Since we're about to to the public.
Yeah, sure. I mean, IGRNS 2, so it's basically a copy of IGRNS. So IGRNS is currently at, well, actually not currently, it's currently at McDonald Observatory. It used to be at Gemini South as a visitor instrument. And it was very successful at Gemini South. So we're moving up. We're the Korean Astronomical Institute decided to build their own and offer it to Gemini. And so we have IGRNS 2 coming in from them. It's basically a copy of IGRNS, similar technical specifications. And basically the idea is you get H and K in one shot, H and K spectra with a resolution of about 45,000. And so this is very important for a number of different science cases, ranging from exoplanet atmospheres all the way to extragalactic high redshift AGN. So it will hopefully, we have the science verification, systems verification run in July, and then hopefully it will be offered for 25A with then it will also, but it will first be offered, I believe, as at least the plan the last time I had heard it was as part of the fast turnaround program in November. So
okay. Oh, so not that long from now.
Yeah, that was the plan as I had heard it the other day, but these things change on a daily basis, so who knows what it will be tomorrow.
Yeah.
So we shall see what happens. But yeah, it's a nice little instrument. and it will hopefully be at Gemini North for a very long time, doing great science. So if you are interested in getting IR spectroscopy on anything, look it up. Yeah, does anybody have any questions about anything related to Gemini? You know, we're definitely we're willing and able to answer those questions. It doesn't have to be about observing. So yeah. And I will say, I know a lot of you applied for the grad visitor program, and so keep applying to it. It should be continuing, hopefully, maybe not this semester, but the semester afterwards. So keep an eye out for it. And yeah, keep applying, get telescope time, come out and visit.
And I guess everybody here is interfacing with Gemini in some way. But do feel free, like after the session, you know, a couple weeks goes by and you're struggling with data reduction, or you wonder when your MAROON-X observations are coming in, or, you know, anything related to Gemini data or the observations themselves or observatory environment. We have lots of points of contact for the observatory. Of course, Zach's your wonderful point of contact for the graduate student visitor program. But every instrument team has a mailing list. You can find this on our public website, and we're all very, very willing to help, give advice. There's a help desk for data reduction for what we call phase 3. So everything after the observation, the contact scientists that you have for your programs, use them, annoy them. I'm actually surprised I don't get annoyed more. You know, we're all here to help make the observations better, and to help facilitate the science that comes out of those observations. So please do feel free to reach out to any of these mailing lists or to us personally as staff if you want to know more information. So I think, Zach, we could call the night if there are no further questions by people here. Was there other things that you wanted to cover?
That sounds good. Any final questions from anybody? If not, then yeah. So again, sorry everyone that the weather did not cooperate tonight. But that's how the observing life goes sometimes. So sometimes you get you know 0.2 arc second seeing, and sometimes you get beautiful seeing but high humidity. So hopefully the next time you all have a chance to see observations at Gemini, it will not be this way. So
yeah, and we're here every night. We're doing Q observing every night, and so I know, Jennifer, you maybe have some observations coming up in a month. We've had a really bad winter and spring, but we're hoping for a better summer. Law of averages helps us out here, and so hopefully we'll be observing. I won't be because this is the last night of my shift, but hopefully we'll have the staff that will be observing under immaculate conditions for the next month straight. We get the rest of the observations that we have planned for the semester. So please do join us on June 11th if you're interested in taking a look at those observations. And otherwise, we'll see you around another time, either as contact scientists or through email or here in person when you apply again to the graduate student program. Thank you guys for joining us. Glad this was a little bit helpful, even if we were closed. And we'll see you next time. Aloha.